For more than 50 years, there's been a mystery about the universe that the greatest minds in physics and astronomy have been unable to solve. The fact that when we map out all of the known matter that we can see and apply the known laws of gravity, it doesn't add up to match the universe we observe. Somehow there are additional gravitational effects that appear, and on a wide variety of scales. In the solar system, the matter we observe explains the gravitational effects we see according to our standard theory of gravity. On the scales of a galaxy, either a new type of unseen matter or a modification of gravity is required. On the scales of galaxy clusters, either an additional massive ingredient or a modification to the rules of gravity is needed. And on large cosmic scales, again, some additional ingredient or some modification to gravity is required. If we seek to add just one new ingredient, cold dark matter can take care of the present mismatch on all scales. If we seek a modification to gravity, the most common one considered is MOND, or modified Newtonian Dynamics, which can explain the first two but requires some sort of additional ingredient or extra modification for the last two. But that's not the only way to try and modify gravity. Moffat's theory, known popularly as MOG for modified gravity, is very different from MOND, and wide binary stars are a newly popular testing ground for gravity. There's a lot to unpack when asking about this, so let's go one step at a time. First to explain Moffat's MOG, then to talk about wide binaries, and then to look at the cumulative case for how we make sense of the universe. If we look at the standard theory of gravity, general relativity, we find that it's built upon a very powerful idea, that the presence of all forms of matter and energy affect the structure of the underlying space-time, and that the curvature and structure of the underlying space-time dictates how all forms of matter and energy move through it. Effects like gravitational time dilation, the cosmological redshifting of light and gravitational waves, and the speed at which individual objects move within gravitationally bound structures are all determined by this theory of gravity, as well as many others. The speed of gravity as well must propagate at precisely the same speed as light, with no deviation allowed. But if the normal, atom-based matter that we intimately know is all there is, general relativity can't explain the gravitational behavior of a huge variety of structures in the universe, including galaxies, galaxy clusters, and the clustering of objects on cosmological scales. The solution astrophysicists normally turn to is the theory of cold, dark matter, which, if we add approximately 5 times as much dark matter as normal matter to the ingredients of the universe, brings all scales back into agreement with observations. No other fix can do that, solve all of these puzzles on all of these scales with just one modification. But still, there are other lines of thinking worth pursuing. The problem with MOND, however, is that it then requires either a different additional set of modifications to the law of gravity or a new type of ingredient that's indistinguishable from cold dark matter to explain behaviors of galaxy clusters and the properties of the universe on cosmological scales. Furthermore, if you choose the first option, an additional set of modifications to gravity, you need yet another modification to either the law of gravity or the ingredients in your universe to explain what we observe when two galaxy clusters collide. You see, when clusters collide, most of the normal matter is present in the form of non-luminous material, gas, dust, and plasma among them, that collides and heats up, whereas the individual stars and galaxies simply pass right through one another. Even though the majority of the normal matter is then in the center of where the clusters have collided, the majority of the gravitational effects observed is where the stars and galaxies have passed through each other, separate from the normal matter itself. Back around 30 years ago, theoretical physicist John Moffat, who was already well known for speculative alternative ideas in theoretical physics such as a variable speed of light cosmology and non-local quantum field theories, proposed a modification to Einstein's gravity that would go beyond the symmetric rank 2 tensor, the metric tensor, that is the hallmark of general relativity, to add in additional non-symmetric terms. Then, about 20 years ago, Moffat reached the point where he could put forth a modified gravity theory that incorporated both scalar and vector terms, both absent in general relativity, that did in fact account for the observed rotation curves of galaxies. In subsequent papers, Moffat showed that his theory can also explain the mass profiles of galaxy clusters, post-collisional clusters such as the bullet cluster, and a variety of cosmological scale observations, although that paper has been through 7 revisions over 5 years and has still to date never been published in a journal, which make it an interesting alternative idea worth considering. In the most recent paper he's put out, Moffat also argues that his MOG theory, in contrast to MOND, agrees with the observations of wide binaries, just as standard general relativity does. Whenever you have stars that are bound together into the same stellar system, you can predict the orbital speed of one star around the other, simply by measuring how far apart the 2 stars are from each other. The law of gravity is simple and straightforward. And just as Kepler's, Newton's, and Einstein's laws apply to the motion of any 2 gravitational objects bound together, 2 stars are just another example of those types of massive objects. When stars are in tight orbits with one another, the velocities of the stars relative to each other are large, and the accelerations are also significant. This is because the gravitational force between them is strong due to their close proximity. However, when stars are in orbits with greater separations, they orbit one another more slowly. These stars are more loosely gravitationally bound and experience lesser accelerations due to the weaker gravitational force acting over a larger distance. And then we have the case of wide binaries. When stars have extremely great separations, they orbit one another at extremely slow speeds, often less than 1 kilometer per second. However, there's an enormous issue with this approach. Yes, in theory, you can use high-quality position and velocity data to infer the orbital data about any type of binary system, and that with data over a long enough period of time, you can infer the orbits of even the widest of binary systems. But in practice, the amount of data you need, the duration of time you need as a baseline for accurate orbital determinations is dependent on the amount of time it takes to make a complete orbit. In our own solar system, for instance, we can determine the orbital motions of Kuiper belt objects at around 50 astronomical units, where 1 astronomical unit is the Earth-Sun distance. But for wide binaries, which are at separations that range from perhaps 2,000 up to 30,000 astronomical units, it would take centuries of data with the current precisions we can obtain. Different groups disagree as to which systems should be included in the analysis, because they disagree as to which systems are legitimately wide binaries, 2 stars separated by a large distance that are gravitationally bound together, versus which systems are simply coincidentally 2 stars located physically close to one another, like 2 ships passing in the night. We don't have the sufficient data to make those determinations for any individual systems, which tells us that the data simply isn't good enough to draw any responsible conclusions. In other words, the science of wide binaries in determining the gravitational behavior of these systems is not yet mature. So, how do we make sense of the universe? You might think that better measurements of wide binaries is going to be the key to resolving this conundrum, but that's unlikely. It will take decades to centuries of data at least before we're able to definitively tell which systems should and shouldn't be included as bona fide wide binaries, and the wider the orbit, the longer the baseline of data that we'll need. It makes a lot of sense that we're doing the best science we can with the novel data that we've acquired, but it's the professional opinion of many, including me for whatever that's worth, that the problem of selection bias, where the conclusions change dramatically, depending on which objects are chosen to be part of the sample, is too great at this moment in time to allow us to draw responsible conclusions about the universe from this approach. However, it isn't premature to note the different realms where the different ideas about our universe make different predictions from one another. A universe with dark matter, a universe ruled by MOG, and a universe ruled by MOND make predictions for solar system scales, intermediate scales, galaxy cluster scales, colliding galaxy clusters, and cosmological scales. However, there's a very big problem for MOG. It has the remarkable property that gravitational effects can appear where the matter itself is not, part of the non-local nature of the theory. This is what enables post-collisional galaxy clusters, which separate the majority of the normal matter from the host cluster that contains the individual galaxies, to have gravity where the mass is not within the framework of MOG. whereas in the dark matter interpretation, the gravitational effects revealed by lensing data are a result of the non-luminous dark matter that is present alongside the individual galaxies. The problem is that we have numerous examples of pre-collisional galaxy clusters in the universe, where galaxy clusters are nearby one another but have not yet collided. Their normal matter is still located within the clusters themselves. In the MOG framework, you should still expect a non-local gravitational signal, where the gravity appears to be affecting regions differently from where the mass is located, whereas in the dark matter framework, you'd expect it to behave more simply as two independent clusters with their own lensing signals. In fact, the data has been in for a long time, for decades, indicating that the behavior is purely local. This is the key observation that poses difficulties for MOG, and arguably the problem area it must address, as well as the currently unresolved issues on cosmological scales that must be overcome. In physics, it's the weakest aspects of your theory that always deserve the most scrutiny, as only the most robust theories will stand up to them all. As we continue to explore and gather more data, the debate between dark matter and modified gravity theories will undoubtedly evolve. But for now, this problem with MOG remains a critical challenge that must be addressed if it is to be considered a viable explanation for the mysteries of our universe.